Good afternoon, class. We are looking at exam 4 review covering chapters 4 and 5 and 6.1. Here's 5.5, the substitution rule, 6.1, areas between curves. All right, so we are going to continue with substitution rule. In the case of a substitution, you are looking for a U substitution, and you're hoping to have its derivative there. Anytime natural log is involved, ln x is a choice of U. The derivative is 1 over x, which makes du 1 over x dx, or dx over x. I want you to pay attention to both notations. They mean the same thing. It's a good practice to rewrite this in a format that it becomes clear what we are dealing with. So I'm going to write this ln x to the second power, and then 1 over x dx. This is u squared. This is du, and therefore we are going to use the power rule on that. 1/3 u cubed plus a constant. Replace the u with ln x, and you're done. Bear in mind, this means ln x times itself 3 times, which is different than ln of x cubed. The integral of e to the power of x minus e to the power minus x over e to the power of x plus e to the power minus x dx. Anytime you have a fractional format, first you want to simplify. This can't be simplified. You use the denominator as u, and notice if you differentiate the bottom, you get the top. The derivative of e to the power of x itself, and the derivative of e to the power minus x is itself, it's -1, which makes du the numerator times dx. We are going to rewrite this such that dx goes up. So we are looking at the integral of du over u. Again, it follows. The answer is a natural log, and of course a constant, and you replace the u. It's ln of absolute value of e to the power of x plus e to the power minus x plus a constant, and you're done. Bear in mind, because this expression is positive, you could replace it with parentheses. All right, we want to do the substitution, evaluate the integration, and use the substitution to evaluate it. This is a definite integral, and there are obviously 2 ways to do that. One way is to go back to original variable. One way is to come up with the new limit. So for now, 25 minus x squared is the more complicated of the 2 polynomials. It's a polynomial under the radical. Its derivative is a negative 2x, which makes du negative 2x dx. So we're going to rewrite this such that x is sitting next to dx. So in a matter of comparison, you see everything is fine. As I mentioned, in most books, they solve for dx. In this case, -2 is missing. So I can put in there because it's a number. And its reciprocal is -1/2. Bear in mind, again, the product must be 1. So this is the -1/2, the integral of square root of u du. I'm not going to put the limits yet. We're going to get to that in a moment. And this is something we've seen many times before, u to the power of 1/2. And that part, 1 over 1/2 plus 1, u to the power of 1/2 plus 1. We don't need a constant because we are evaluating. And 1/2 plus 1 is 3/2. This is 2/3. The product is -1/3. And now I can go back to I do the reverse substitution. I can go back to the fact that u is 25 minus x squared, and therefore use the original limits. That's fine. However, the second method is to figure out the new limits. When I put the 3 here, x squared, 3 squared is 9. So 3 squared is 9, 25 minus 9 becomes 16. If I put the 4 here, 4 squared is 16. 25 minus 16 is 9. So those are my new limits. And I'm going to stick with the new limits. Normally, new limits are easier to deal with, and You keep the negative 1/3 outside to make life easy, and you raise 9 to the power of 3 halves minus 16 to the power of 3 halves, and square root of 9 to the third power means 3 cubed, or 27. Square root of 16, which is 4 cubed, 64. Their difference is negative 37. With negative 1/3, we get positive 37 thirds. So a quick recap: when you have a definite integral, which is a number, and you are going to use a substitution, you can always go back to the original variable. Bear in mind that you can't use the original limits for the u. That's why I didn't put anything there. But I can evaluate it, and with the u, I use the new limits. You can do it either way. All right, so we are going to move on. As I mentioned, whenever we deal with a natural log, that is the choice of you. Whether we are going to evaluate it from 0 to 1 or not, it makes no difference. You need a substitution, so let u be the natural log of x plus 1. Now, if I want to differentiate, this is 1 over x plus 1 times 1, or simply 1 over x plus 1. So du becomes 1 over x plus 1 dx. I'm going to rewrite this so it becomes clear what we have. So I'm going to write this part, dx over x plus 1, in this format. And I do it on purpose. I want you to see this seems different than this one, but this is identical to this one. So I want you to get used to it. Therefore, you're dealing with the integral of u du. Again, I didn't put the limits. Why? Because I have to figure it out. So if I put the 0 in here, I get ln of 1, which is 0. If I put 1 here, I get ln of 2. So those are the new limits. Of course, the integral of u, du is half of u squared. So plug in ln2, plug in ln1. ln1 or 0 doesn't do anything, just ln2, and it's half of ln2 quantity squared, and you're done. It's an exact answer, and we're going to keep it as an exact answer always. Evaluate the integral of negative 2 to 2x to the power of 6 plus 1 dx. Well, we can do that, but I want to go over an important theorem, and that is the integral of symmetric functions when f is a continuous function in the interval of minus a to a. If f is odd, f of minus x equals minus f of x. That's the meaning of odd. The integral of minus a to a f of x dx equal to 0. So pay attention to this one. This graph, in essence, shows it. If it's an odd function, I hope you recognize this area and this area are the same, but they undo each other because this is considered positive, this is considered negative. On the other hand, if f is even, so this is odd. Odd means symmetric with respect to the origin. If it's even, that means symmetric with respect to the y-axis. That means f of minus x equals f of x, the integral of minus a to a f of x dx. You can evaluate it from 0 to a instead of minus a to a and multiply it by 2. So as you can see, if you want to go from minus a to a, the right side and the left side are identical. You evaluate this one, you multiply it by 2. And the reason it's important, because most of the time it's a lot easier to evaluate from 0 to a number rather than a negative number to a positive number. In this case, we recognize this as an even function. F of minus x equals f of x. So this is f of x. So you really have to show, by the way. So if I'm looking at f of minus x, that means minus x to the power of 6 plus 1, which is x to the power of 6 plus 1, which is the same as f of x. You have to show that, everybody. You have to justify your answer. And so with that being the case, we are going to evaluate it instead of negative 2 to 2. We're going to evaluate it from 0 to 2 and then multiply it by 2. Again, because it makes it a tad easier. So again, when one of the limits is 0, it's easier to do that. So this is 1 over 7x to the power of 7. This is x from 0 to 2. And then don't forget to multiply by 2. Of course, 0 doesn't do anything. You plug in 2. 2 to the power of 7 is 128 divided by 7 because of 1/7 plus 2. So this is going to add up to 284 divided by 7. Just for the sake of argument, you multiply this one by 2. You get 256. Multiply this one by 2. You get 4 or 28 over 7. That's how you arrive at this answer. It's elementary. All right. When you come across an integral which is almost impossible to do, you're hoping it's an odd function and it becomes 0. So f of x is this. We're going to evaluate f of minus x. Tan of minus x becomes minus tan x, and the bottom is completely even, so it doesn't make any difference. Minus x quantity squared is still x squared. Minus x to the power of 4 is the same. So f of minus x equals minus f of x. F of x is an odd function. So we have to prove this is an odd function, and therefore, by the theorem, it becomes 0. And we just proved that. All right, we are ready to move on. We can model the rate of airflow into the lungs by the function f of t is 1/2 sine 2 pi over 5 t liters per second. So that's a rate. That's the derivative function. Where t is the time in seconds, find the total amount of air inhaled in one cycle, known as the tidal volume, if the cycle lasts 5 seconds. Now, note the time for inhalation is half of the cycle, 5/2 seconds. Total amount of air would be the integral of 0 to 5 over 2 f of t dt. This is the accumulated change, the net change theorem. Plus, we are assuming the amount of time it takes to breathe in and breathe out. We are assuming they are identical. So if it takes the whole cycle takes 5 seconds, each one of them takes half of that. That's why we have the 5/2. So we are going to put this here and take the integral from 0 to 5/2. Of course, times dt. All right. Whenever you want to integrate a sinusoidal function, you look at its argument. If the argument is x or t or theta, so be it. Otherwise, the argument is the choice of u. So the argument 2 power 5 times t is the choice of u. The derivative is 2 power 5. In other words, du dt is 2 power 5, which makes du 2 power 5 times dt. So let me rewrite this. This 1/2 inside or outside the radical makes no difference. I keep it outside. I put sine of 2 power 5 times t, and I have a dt, and I compare it to this one. Again, 2 power 5 is a number class. Again, in most texts, they're going to solve for dt. I'm not going to do that. 2 power 5 is a number is missing here. So if I put 2 power 5 here, I can undo it with its reciprocal 5 over 2 pi. So 2 power 5 and 5 over 2 pi. So the result is this is 5 over 4 pi. This is sine of u du. And the limits, I'm not going to write it yet because the limits are not the same. We're going to figure it out in a moment. But this is sine of u du. Now, what are the new limits? Well, plug in 0. Let me use a different color. Plug in 0 and you get 0, right? You mean, so you're going to change the t. Plug in 5 halves, so we get 2 pi over 5 times the t, which is 5 halves. And that's pi. The derivative of sine is cosine. The integral is negative cosine, and we keep the 5 over 4 pi. We're going to go from 0 to pi. We are going to take the negative sign out to make life easy, everybody. And then cosine of pi minus cosine of 0. So we took the negative sign out. Cosine of pi is -1 minus cosine of 0 is +1. So -1 minus 1 minus 2. So that is 10 over 4 pi or 5 over 2 pi. This is an exact answer, everybody. Now, this entire thing is an approximation. So roughly 0.796 or 0.80 liters. This really depends on how many decimals they ask you. As far as the units, the rate was liters per second. That's why this is in liters. So it should be clear as to why this is the case. Okay, everybody. All right, so what happens when we are dealing with sinusoidal functions? Well, if the argument has an exponent, if the argument is not just a simple x, t, or theta, that is the choice of u. The derivative is 2x, which makes du 2x dx. We are going to rewrite this such that this is sine x squared, and this one, everything is in order, except 2 is missing. So what do? 2 is a number. Again, you can solve for dx, but instead I'm going to put the 2 and undo it with a 1/2. So we end up with 1/2 sine u du, and the derivative is cosine, but the integral is negative. So negative 1/2 cosine u plus a constant. And u is replaced by x. That's the final answer. And as always, you can differentiate and it gives you the same answer without the dx, and that's how you check it. What happens? We have both sine and cosine. The one that doesn't have the exponent, the one that does have the exponent is a choice of u. Without the exponent, in this case, is sine x. The derivative is cosine. So du is cosine x dx. We are looking at the integral of u squared du using the power rule on that. 1/3 u cubed plus a constant. Replace the u and we are done. 1/3 sine cubed x plus a constant. What about this case? Again, we have sine and cosine. But this time it is cosine that has the exponent. Therefore, u is cosine x. The derivative is negative sine, which makes du negative sine x dx. So we are dealing with this, okay, both of them. And so we notice that we have sine x dx, but we don't have a negative. So we're going to put a negative next to it and the negative outside because the product of negative times negative is positive. In essence, we put in -1 in, -1 out. So now we are looking at minus u to the power of 20 du. And again, that is using the power rule, -1/21 u to the power of 21 and a constant. And you are going to replace the u with cosine, and we get -1/21 cosine to the power of 21x plus a constant. A quick recap. If you're dealing with sinusoidal functions, when the argument is not basic x or t or theta, that's a choice of u. If you have sine and cosine, the one that has the exponent is the choice of u without the exponent. Sine x in this case, cosine x in this case, and the rest is fairly straightforward. What about tan x? What is the integral of tan x dx? We use trigonometric identities and change the tangent to sine over cosine. And a fractional format, when you can't simplify the denominator, is always the choice of u. You know the derivative of cosine is negative sine, so du is negative sine x dx. So we are going to rewrite this so it becomes clear what we are dealing with. We are dealing with 1/cosine x, and we are dealing with sine x times dx, and we're going to put -1, so here, and -1 here, to make sure this sign is taken care of. So what we are looking at is minus 1/u du, and 1/u, of course, the answer is a natural log. So we get minus natural log of u plus a constant, and u, we can replace it with cosine, everybody. Now, if you remember the power rules, you can say ln of cosine x to the power of -1, which means 1 over cosine x, which means secant x. So natural log of absolute value of secant x plus a constant that has got to do with properties of logs. Very straightforward. 6.1, the area of the region between two curves. Let f and g be continuous functions with f of x larger than or equal to g of x over some interval of a2. Then the area of the region between the two curves from x equals a to x equals b is given as follows. And I'm reminding that the area under a curve, it uses the Riemann sum. Everybody remembers that. So the idea is that area of the region between f and g, this area. So this is f, this is g, and f is above g. That's what this means. F is above g. This one is area under f only. This one is area under the g function only. So if you want this one, is this area, the integral of a to b f of x dx minus the integral of g of x dx from a to b. So subtract the red one from this green one to get this. Very straightforward. So that's the region. So you write the answer is the integral of a to b, parentheses or brackets f of x minus g of x dx. And you evaluate it from 2. We are assuming f is at top of g from a to b. F is larger. So the area of the region between two curves process. Number one, graph the two functions. So if they give you functions, you have to graph them. If they didn't give you the graph. Find the points of intersection by setting f of x equals g of x and solve. Evaluate the integral. And the way we do that, first, we come up with an increment of an area. This is called an increment of the area. This has the height. This has the width. The width, I'm going to call it dh. What happens as far as the dh is concerned? It either moves along the x-axis and ultimately becomes dx, or along the y-axis and it becomes dy. It's only one of those two. However, we go with dh to figure it out. Okay, we have to figure out which one is which. That's why I don't want to start with any of it. And again, I think that, so notice this one. And by the way, this width is extremely small. So for all practical purposes, if you look at the thickness, the left side has a height, the right side has a height, and obviously they are not the same. But if width is small enough, the left and right are almost having an identical height. This is the area of a typical rectangle is y of the t, that means y of the top, t stands for the top, minus y of the b, that means y of the bottom. In this graph, the y here comes from f of x, y of the top. Y of the bottom comes from the g of x, okay? So, dA, this rectangle, and again, the thickness, we made it large enough for the sake of argument, so we can see it. Otherwise, this big, This width is almost nothing. That's the idea. Okay, and goes to infinity. This is delta x or delta y goes b minus a over n is almost zero. So h times dh, and again dh is either dx or dy. So the integral of a to b h dh, if the typical rectangle is from left to right, it's x of the right minus x of the left dy from a to b. If it's like that, y of the top minus y of the bottom dx, the integral from a to b. That's the idea. Let's make some sense out of this by looking at a couple of examples. And of course, a to b f of x minus g of x dx in this case, right? Again, we are looking at this one for this question, for this graph. For this one, we are looking at this one. Y of the top. T stands for the top minus y of the bottom. So having said that, let's look at this example. We want to find the area of the region bounded by y equals 2x squared minus 3x plus 2, and the x-axis x equals 0 and x equals 2. The very first thing you have to draw, and I'm going to assume everybody can draw that. Of course, this x equals minus b over 2a is the location of a x-axis for the vertex. You plug in x coordinate for the vertex, you plug in, you can find the vertex, and you can see that this opens up, and so on and so forth. So this is the graph, and from x equals 0 to x equals 2 means we want this. That's the area we want. So what we do, and this is the vertex. Again, vertex x equals minus b over 2a and so forth. What we do, we draw a typical rectangle looking like this. Please understand again, this is the width, this is the height. The width is very small. We are showing it really, really thick so everybody can make some sense out of it. So if you look at this rectangle, the area for this rectangle is it's the width times the height. So what is the height? The height is the y coordinate. Okay, so this point has a y coordinate. This point has a y coordinate. And h, dh is y of the top minus y of the bottom. And the reason is dx, look at this thickness. This rectangle has to move, sweep across the x-axis to cover this. Just this one, move it here, 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 here. As it's moving along the x-axis, creates the widthness dx. So this is dx. So what is y of the top? Comes from the function. What is the y of the bottom? Comes from the x-axis, which is 0. So it's f minus 0. F or y. By f, we mean this function, okay? So y of the top is this, minus 0. And all you have to do, integrate this from a to b. From a to b. That's all. So the area is the integral of a to b h dh. And h is this, dh is dx. And that's the hardest part. Now everything else is now easy because we know integration and we should have no problem finishing it off. A quick recap. You draw the function. Here's the region you want. You draw a typical rectangle. This rectangle, you move it along the x-axis, and that means dx is the width. The height is y of here minus y of here. Y of the top comes from the function, and y of the bottom comes from the x-axis, which has the equation y equals to x-axis, everybody, y equals to. All right, so that's it. Because if you understand one question deeply, the rest of them follow easily. So this is 2/3 x cubed minus 3/2 x squared plus 2x from 0 to 2. 0 doesn't do anything. You plug in 2. 16/3 minus 6 plus 4. And this is negative 2. Okay, with this becomes 10/3. I'm assuming evaluation is elementary, so we don't worry about that too much. Find the area of the region bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. First of all, g of x equals x is a line through the origin, right? This one, x squared opens up, minus x squared opens down, and it goes up by 2 units. So we have no problem with the graph. So that's the first thing I want everybody to notice. So we have the graph. Now we draw a typical area looking like that. Remember, we want the area of the region bounded. This is the area that we want, everybody. And I'm going to erase it because, this is the area we want. Okay, look, this is the area, the shaded region, right? And this is a typical rectangle. And the rectangle has a width and has a height. Now, we need to know after we graph what are the limits of the integration. These 2 points we need to find, which means we're going to set them equal and solve first. So we know the limits and then we take it from there. So set these two equal. So we're going to set f of x equals g of x, these two equal. And since we want to solve a quadratic equation, we're going to take everything to the right to make sure this is positive. We can factor it into x plus 2x minus 1. So there are two answers, negative 2 and positive 1. It's easier to use this one. G of x is x. So negative 2, negative 2, 1, 1. Those are the points. And you can, by the way, you should really check it with this one also. So those are the points. So we know the x coordinates for those 2 points and the y coordinates. And so this one is a typical rectangle which has the width. And if you look at this rectangle, if you move it, how do you move it? You move it along the x-axis, this way and that way, left and right. So this creates the width of delta x. And the height is from here to here. At any given point, the height comes from the curve minus the line at any given point. So dA is y of the top minus y of the bottom times dx. That's an increment of an area, a typical rectangle. Y of the top comes from the curve. So y of the t or top is this, minus y of the bottom is this. So 2 minus x squared minus x. Therefore, the region that we are interested in is the integral of this piece going from the x coordinate of their intersection, negative 2, to this x coordinate, positive 1. This is 2x It's minus 1/3 x cubed minus 1/2 x squared, going from -2 to 1. I'm going to leave it for you to come up with 9/2. You plug in 1, you plug in -2. You should have no problem getting the answer, everybody. So I'm going to leave it for you to come up with the answer. A quick recap. First, you graph the two functions. Then you draw a typical rectangle, and you notice this rectangle is going to move this way. So what are the limits of integration? You have to find the points of intersection by setting them equal. You find the points of intersection. And the height is the y of the top minus y of the bottom, which is the y of the top coming from the curve. The bottom comes from the line. We're going to graph these two. In order to find the area, the very first step is to graph. And I hope you remember, when you're dealing with x and y, and one of them has exponent 2 is a parabola. Because y is squared, it's a parabola that opens sideways. Because this is negative, it opens to the left. I'm going to leave it for you to graph this. So this is the graph of x equals 3 minus y squared. Now, y equals x minus 1 or x equals y plus 1, the graph is a line, and it looks like that. Now, there is a reason that I mean, for graphing, you don't need that, but there's a reason that I did that. I'll explain it to you in a moment. So what we want, the area of the region bounded by the graphs, we want this area. In other words, we want this area, right? What happens is that this function, this is the curve, we call it f of y equals, this line is f of y equals y plus 1. And the curve, we call it g of y equals 3 minus y squared. Notice that you have to find the points of intersection by setting them equal first. That's the first thing we need to find, points of intersection, everybody. And to do so, set them equal. 3 minus y squared equals y plus 1. That's one of the reasons we changed it. And if I take everything to the right, this becomes y squared plus y, and this becomes minus 3, with plus 1 becomes minus 2. Again, it's a simple factoring, everybody. It factors into y minus 1, y plus 2. So y is 1, y is negative 2. Now, it's important to know if I want to draw a typical rectangle, and so those are the points of intersection. If I want to draw a typical rectangle, it's going to go like so. It's not going to be, so this will be sweeping up and down to cover the entire graph. You're not going to go this way. And here's the reason, by the way. If you put, and I'm going to put two of them so you see why we can't go that way. If you pick a typical rectangle here, it works. The top is the line, the bottom is a curve. As you move this across, everything is okay until we hit this one. And if we go to the right of that, let me use a different color. So here, what happens here? Now this one, remember, you're moving this, okay, until you cover everything. This one, the top and the bottom are both the curve. That's why it doesn't work. However, in this case, all the way from here to bottom, anywhere you go, it would be x of the right minus x of the left. So dA is x of the, let's put a pointer for you. So let me actually erase the rest of it because I don't, anyway. So x of the right minus x of the left. That will create the height, which is the right one is the g function, the curve, and the left one is the line f. And so x of the right minus x of the left. X of the right is 3 minus y squared minus x of the left is y plus 1. We are going to take the integral of this from, now it's going to go up and down. So the limits of integration come from the y coordinates from -2 to 1. So pay attention to this and why we are using those coordinates from -2 to 1. Now this one, let me rewrite this. This one is minus y squared. This one is minus y. This one is minus 1 and 3 plus 2. Okay, so first you rewrite it in this fashion. Okay. And now you integrate. This is -1/3 y cubed, -1/2 y squared plus 2y, evaluated from -2 to 1. Again, I'm going to leave it for you to do so, and you get 9/2. Now, a quick recap. After you graph, you notice that a rectangle that you come up with can go up and down. If you go this way, it's not going to work out. So up and down, that means you need functions of y. That's really the idea. And this, the width, the thickness is dy, but the height, if you will, is x of the right minus x of the left. Find the area of the region that is bounded by the graph of f of x equals 2x plus 1, g of x equals x squared minus 1. And I'm going to assume nobody has any problem graphing a line, or y equals x squared and then shift it up by 1. So that shouldn't be any problem. Everybody can graph. So the first step is to graph easy graphs. So the next step is to find points of intersection, and that means f of x equals g of x. We are going to set them equal. 2x plus 1 is x squared plus 1. We can cross the 1, x squared minus 2x, and x is either 0 or 2. I'm assuming nobody has any problem with the methodology. Okay, so x is either 0 or 2, which means we have the two points of intersection. 0, 1 is one of them, 2, 5 is another one. Now, we want to evaluate the integral, and that means I need a typical rectangle. So I can draw a vertical one where this rectangle can sweep across the x-axis, meaning the width is dx, but the height is y of the top. Let me put a dot here. Y of the top coming from the line minus y of the bottom. So we have y of the top minus y of the bottom. And that means this, right? F minus g, where f is the function 2x plus 1, and g is the function x squared plus 1. And so 2x plus 1 minus x squared plus 1 dx. And we take the integral of that from the x coordinates from 0 to 2. X coordinates of the 2 points. X coordinates of the 2 points. I can't emphasize this enough. So this one is minus x squared minus 1. I put them, they cancel each other. 2x minus x squared. And this is x squared. This is minus 1/3 x cubed from 0 to 2. Now you plug in 0, doesn't do anything. Just plug in 2. You get 2 squared minus 2 cubed over 3. This is 4, this is 8/3, and it becomes 4/3. And believe it or not, you're done. However, I chose this question because it's somewhat different than the others, and we can look at something very interesting here. Here's the second method. If we go this way, what happens? Notice if you sweep this up and down, always. So we have, what color do I want to use? This one. This one, no, actually. Yeah, I guess that's fine. So this is x of the right, this is x of the left, and it will always be like so. This is, see, the line is always above the curve is always on the right side. So you can do both methods. So here's the method 2, f of x. So this is g minus f. That's the height. And so we have x of the right minus x of the left times dy, because this is going to sweep along the y-axis. So we write those, and we want to solve for x. This one is easy, class. You can move the 1 and divide by 2. This one, you can move the 1 and take a root. Please understand that this one is very straightforward. This one, there are 2 parts. The right side of the curve is this. The left side is the same thing with the negative in front of it. Therefore, we are ready to work on that. So we have the integral now. The limits of the integral now would be the limits. Let me erase my work so we can. So the limits of integration now, because we're going to go from the y coordinates of 1 to 5, okay, because this green one goes up and down, everybody. So from 1 to 5, okay. And then what is the right side? It's always the curve, this one. What is the left side? It's always the line, this one. And you are going to integrate that one. This one is, by the way, y minus 1 to the power of 1/2. And this, believe it or not, uses the u substitution, let u be y minus 1, and integrate it. So I'm going to leave it for you to finish that. If you have a question, you can ask me. This part, you let u be y minus 1, and du becomes dy. And so you're looking at u to the power of 1/2, which is 1/1/2 plus 1. u to the power 1/2 plus 1, and this becomes 2/3 y minus 1 to the power of 3/2. This one is 1/2. You keep it, minus 1/2. This is half of y squared. This is minus y from 1 to 5. I hope everybody can do this. This is integration, everybody. And you're going to plug in replace the y with 5. So this becomes 4. Replace the y with 5. This becomes 25. This becomes 5. And then you replace it with 1. When you replace it with 1, this goes to 0. This is 1, so 1/2. And then this is 1. And when you finish the job, this is 16/3 because square root of 4 is 2. 2 cubed is 8. Times 2 is 16/3. This is minus 15 over 4 because 25 halves minus 10 halves. Okay, 15 halves with the negative 1/2 is negative 15/4. And this entire thing, this is 0, has no bearing, negative and negative positive 1/4. So if you put them all together, you get 16 over 12 or 4/3. You get exactly the same answer. I highly recommend you work on this to make sure that you have no problem with that. Here's the last question. Find the area of the region between the graphs of f of x equals 3x cubed minus x squared minus 10x and g of x equals minus x squared plus 2x. The very first step is the graph, and you can even use a calculator for that, but that is something that has to be done. You have to graph the function. So as you graph the two functions, f of x is the cube function. So this is the function. Maybe I use some color on that. Let's see. So this is the function, everybody. Okay. And the parabola that opens down is the other function. Okay. And we want an area between the two. So this area and this area, and they have the top and the bottom in this case versus this case are different. As you look at them, one is the cube function, one is the quadratic function. The very first thing is to set them equal and find points of intersection. So we graph them, we're going to set them equal. You don't have to move this, they are identical. So we can cross them out. If we move this, becomes negative, and negative 10x becomes negative 12x. And we set it equal to 0 by factoring the 3x out. And this is x minus 2x plus 2. Therefore, we have three answers. X is 0, x is 2, x is minus 2. So we have three answers, negative 2, 0, 2. And you put those into one of them, and you find the y coordinates. Let me erase my work because it's messy. And those are the 3 points of intersections. Negative 2, if you put in, you get negative 8. Actually, you should check with both of them. 0 results in 0, 2, 0. Now, to evaluate the integral, you throw in a typical rectangle. In both of them is y of the top minus y of the bottom. But what is the difference? Let me see what color will do the job here. The top here comes from the cube function. The bottom here comes from the parabola. Whereas, let's see what color now. Be red. Over here, the top comes from the parabola. The bottom comes from the cube function. So f minus g, and I wrote it here because we're going to use that. F minus g is used for here. So look at this, and we're going to use the absolute value here. That's the concept, because we want the area. This is f minus g, which is this function, 3x cubed minus 12x dx. We worked it out. But this one is g minus f. So it's the opposite of that, minus 3x cubed plus 12x. In this case, we are going from here, this point to this point. That's why we go from -2 to 0. In the second case, we go from this point to this point. That's why we go from 0 to 2. This one goes from 0 to 2. So I hope you see how we arrive at the limit. So this one is 3/4 x to the power of 4 minus 6x squared from -2 to 0. This one is now the same thing, but negative. The same negative. Negative 3/4 x to the power of 4 plus 6x squared from 0 to 2. And you can evaluate each one, add them up, and the result will be 24.